Today, we're going to talk about two different subjects. So basically, in any machine learning course, it's kind of customary to go over some basics, first of all. So today, we're going to work a little bit on probability. So this is going to kind of serve as some refresher for your knowledge of probability. It's by no means a comprehensive probability class. And then in the second half of today, we're going to talk a little bit about linear algebra. We're not going to go over a lot of proofs and things that you've probably seen in a linear algebra course. What we're going to do probably is going to be mostly hands-on. So we'll show you how to kind of implement those linear algebra math in NumPy. And it's kind of going to be similar to what you will be doing in your first assignment and also other assignments that you have. So I'm just going to start with probability today. Again, as I said, we are assuming that you have already passed the course in probability and also linear algebra and also Python programming. So if you think your mind is not refreshed on these materials, I think these few days that it's a holiday is going to be a very good time to read about them. We have shared also some very useful material on the course website. So after today, if you still feel you need to do a little bit more exercise, I'll highly recommend you to check them out, which is on our course website. So the plan for today for the probability part is like this. So we'll quickly go over some probability basics. Then we'll talk about conditional probability and Bayes rule, which you probably have heard about it. And it's something very important, and we're going to use this a lot throughout this course. Then we'll talk a little bit about random variables, some concepts such as independence, expectation, and variance. And then we'll talk about high dimensional probability. So basically what's going to happen if you have multiple random variables. And this is probably the most relevant part to our course. Basically, you can think about machine learning as just another way of expressing high dimensional probability. And finally, we quickly go over some important distribution functions, which we will use a lot throughout the course. And from then on, we'll assume that you know these. Okay, so let's go over some basics. I hope that you are familiar with what I'm going to talk about. If not, again, I highly recommend you to probably go over those material or even watch some YouTube video or take maybe a very short course on probability. So to define a probability, we are going to talk about three things at first. So first thing we're going to talk about is sample space. It's customary to show it with uppercase Greek letter omega. So essentially think about random events such as rolling a dice. The set of all possible outcomes, which in our case is going to be just numbers from 1 to 6, is going to basically be our sample space. So the sample space is the set of all the actions, all the outcomes that you might see. Then we have another concept, which we call it an event. So you can think about an event from a mathematical perspective as a subset of this bigger set sample space. So again, in the case of rolling of dice, so we basically have 6 faces on a fair dice. And the idea is that we can define event as being, for example, just a number 1, or we can define it as being something like we see an even number or an odd number, or we can even describe the event as being the whole sample space or nothing. Basically, so any subset of this sample space, which can also include the sample space itself, and it can also include nothing, is going to be an event. And finally, the probability that we'll kind of formally define at this point is essentially a number that we assign to this event. So now this is not any number. So as you probably have known before, for a function to be a probability, it needs to satisfy a few axioms. So formally, there are only 3 of these axioms that needs to be satisfied. We call them properties here. They're different from axioms. So for those of you who are like hardcore math students, axioms are completely different from properties. So the idea is that this probability value should be between 0 and 1 inclusive. So it can be 0, it can be 1. The probability of the sample space is essentially 1. So the probability of seeing all the possible events is 1. You cannot see something that is not in the sample space, essentially. And the other very important part, which is also one of the axioms, is that if you have events that are mutually exclusive, which we'll talk about what this means, you can actually find the probability of their union by just adding the probabilities. So now let's talk a little bit more about this last one, because this is probably a little bit more difficult than the other two. So the idea is that if you have a bunch of events, you can define two operations for like these events. One operation is basically the intersection of the events. So the intersection, if you're familiar with programming, is essentially what AND represents in the programming world. So when we say A intersection B, we mean that both of them, A and B, should happen at the same time. So basically, the probability of both events happening at the same time is less than or equal to the probability of the minimum of those values. So let's say you have two very rare events. The probability that both of them happen at the same time should be less than or equal to the probability of the rarest event that you have. And then we can also define another operation, which is called the union. So again, just following our example of programming, you have an operator called OR. And OR is basically satisfied whenever one of these two events are happening. So A union B is basically the set of all events that satisfy either A or B or both at the same time. So essentially, we can talk about this as being the union. And what the third axiom represents is that if you have a bunch of mutually exclusive events, and this is probably the first definition that we'll talk about, and then we're going to also talk about independence. Some people mix them up. Don't be that person. So when we have a bunch of events, let's say we have n events, we call them mutually exclusive if the intersection of those events pairwise is going to be equal to 0. So essentially, the two events cannot happen at the same time. A very good example of it is day and night. So if it is day now, it cannot be night. So because of this, we call these mutually exclusive because they cannot happen at the same time. And now if you have a bunch of mutually exclusive events, if you want to find the probability of union of them, you just add their probabilities. So this is an axiom. So we assume this is true, and then we build everything on top of that. But intuitively, you can kind of agree with that, I guess. Okay. And finally, the last property that we haven't talked about is that if you have two events where one event is a subset of the other event, then we can say that the probability of the smaller event, the event that is like the subset, is always less than or equal to the probability of the larger event or event B. So again, in the example of the roll of a dice, so for example, let's say probability of having an even number is going to be P of B. And probability of seeing 2 is going to be A. So 2 is a subset of all those even numbers. So essentially, probability of seeing 2, which is 1/6, is less than the probability of seeing an even number, which is 1/2. Do you have any questions from the probabilities or like the properties? Are they good? Pretty easy? Okay. So now that we know a little bit about these, let's go and talk a little bit about conditional probability and the Bayes rule. So conditional probability is a very important concept in this course. We're gonna touch on this in a lot of algorithms that we'll discuss. And hopefully by the end of today, what we want you to have, if you haven't already, we want you to actually develop some sort of intuition of what is a conditional probability and how is it like different from A intersection B. So from now on, instead of saying A intersection B, I'm just gonna call it the joint probability of A and B. So this is how most like advanced courses and most advanced books talks about. When we say joint probability, we just mean the intersection of the probabilities. And the probability of A given B is going to basically be the probability of the joint of A and B divided by the probability of B. So, and the name that we call this is that, so we call B the evidence or the observation. So basically, we condition A on observing B, and that is going to be equal to the probability of seeing both of them at the same time, divided by seeing the evidence, basically. So just to give you an idea, let's say I'm telling you that one of my friends is there, and he's got, oh, I don't even specify their gender, and they will come here. And I want you to give me a number or bet some money on that person being 6 feet tall or above. So what is going to be your money? What you're going to do probably is going to be going over the internet, seeing how many people have like the height equal to 6 foot or taller, and then you divide it by the population of the world. But if I give you some more information about that person, for example, if I specify their gender, I tell you that they're playing in the NBA, they are like professional basketball players, then your probability of that person being 6 foot or taller is going to increase. So essentially, this B, this evidence, changes your perception of the probability of A. So in this context, and this is going to be something we'll see a lot in machine learning, because in machine learning, usually we want to like find the probability or like estimate a variable. And first we have no idea about that variable. And then we see some observation, we see some data about it. And then our job is basically to develop a model to change this probability. So that's why we usually call P of A the prior probability, because it's the probability we assign to the event A without seeing anything. It's basically our prior belief. And then this B is going to be our evidence, and the probability of A given B is going to be our posterior probability. So we observe an event, we observe some evidence, and then our probability about event A will change based on our observation. And the function that defines how it's going to change is basically the probability of seeing them at the same time divided by the probability of B. And using the same formula, we can just change A and B, and we get another formula like this. And since P of A intersection B, or the joint probability of A and B, is equal to the joint probability of B and A, we can also have this funny looking formula. So essentially, what we call this is the chain rule of probability. It will make more sense when we talk about high dimensional probabilities, but it essentially tells you if you have the conditional probability of A given B, or B given A, and then you have the probability of the evidence, which in the first case is probability of B, the second case is the probability of A, you can find their joint probability using this formula. So all you need to do is to multiply the posterior probability with the probability of the evidence, and suddenly you have the joint probability. And the way you can kind of think about it is this. So when I give you some evidence about an event, like someone being 6 feet or taller, your sample space kind of changes. So instead of dividing that number by, let's say, the population of the world, you will divide that number by how many NBA players are out there. Because I don't know, like how many NBA players are 6 feet or taller? Probably above 90% of them. So now your probability drastically changed with this new information. And the reason for it is because you are changing both this joint probability and also this denominator. You're essentially by making this smaller. So if I give you an event or if I give you an evidence that is very rare, like someone being an NBA player is probably a very rare probability in the world, that will increase that posterior probability significantly. And that's why these rare events are important. So enough talking with the conditional probabilities. So a mathematician called Bayes actually did some calculation using the conditional probability and came up with this formula, which we now know as Bayes' rule. So essentially what we can do is instead of having PA intersection B, we can replace it with the probability of B given A probability of A given B multiplied by P of B. Because if you do it the other way around, they just cancel out and you just get PB given A equal to PB given A. So by just using this funny trick, you will have a new formula. So essentially here, it says P of A given B. So probability of A given B is equal to, now this numerator is essentially, again, the joint probability, but now we factorize it, we rewrote it as P of B given A multiplied by P of A. And then the denominator is the same. So you probably have seen these questions before if you've ever taken a probability course, that they tell you that, oh, like, for example, we've developed a COVID test. So this test, for example, if you have COVID, it will tell you 99% of the time that you're positive. If you don't have COVID, it has some error, 10% of the time it tells you positive. Now you tested positive for COVID. What is the probability that you actually have COVID? And these are the times that Bayes' rule is very important for us. And the other thing that we should touch on before continuing is another important rule in probability, which is called the law of total probability. So essentially, we can also rewrite this P of B because, you know, writing the probability of the evidence is not as easy as it seems. So in many cases, like the question that I just told you, like what is the probability of having a positive COVID test? This is usually very hard to find. But instead of that, we can actually, again, do a very clever factorization and write it like this. So just bear with me. I'm going to describe to you what does it mean. So the first term, again, from the last slide, we know that the first term is going to be the joint probability of A and B. So the probability that A and B happens at the same time. Now, the second term is going to be the joint probability of B and A prime or A complement. So by definition, A prime or A complement is, as the name suggests, the complement of the event A. So A and A complement are two disjoint events. And if we find the union of them, we get to the sample space. So you can think about it as people having COVID or not having COVID. So you can kind of divide everyone in the world based on if they have COVID or if they don't have COVID. People who have COVID are separate from people who don't have COVID, so they're mutually exclusive. And all of them combined, the union of all of them is going to be the sample space, the whole world. So if you can somehow find a way to divide your sample space into a bunch of basically mutually exclusive events, you can write that probability, the probability of seeing that event B, as like the law of total probability as this. So again, this is for two events, two disjoint events. If we had more than two disjoint events, we would add some other terms here, like P of B, I don't know, given A1 times P of A1 plus P of B given A2 times P of A2, P of B given A3, P of A3, and so on and so forth. So that is also a very helpful probability law because in many cases, as I said, it's not that easy to find probability of the evidence right off the bat. So what you need to be doing is you need to kind of factorize it in this way. And then the final formula that we get is going to look something like this. So now there are tons of questions on Bayes' rule that just uses the same formula. Again, if you want to find out if you actually have COVID or actually have a disease, given you got a positive result, this is the way to kind of find it. And we use this again a lot, like essentially like the conditional probability is something that you will use a lot throughout this course. So if you don't feel really comfortable with it, try to solve a bunch of questions so that you feel that you're ready to actually tackle it in the course as well. Okay, any questions? All good? Perfect. So now let's go to our next topic, which is the independence. So first of all, before talking about independence, again, remember we had another definition kind of similar, which was two events that are mutually exclusive. If two events are mutually exclusive, the probability of their intersection is equal to 0. So if you observe one event, you are sure that the other event has not happened. If it's day now, the probability of being night is equal to 0. So just have that in mind. Now we have another concept between two different variables, which is called the independence of variables. So when two variables, A and B, are independent, the joint probability of A and B is equal to P of A times P of B. Or the way that I like to put it is using the conditional probabilities. So just doing some linear, like doing some algebraic manipulation here. P of A given B is essentially P of A and B divided by P of B. And based on this definition of independence, P of A and B is equal to P of A times P of B. So the P of B's will cancel out, and you will essentially have P of A given B is equal to P of A. So I want you to see independence in this way, that if you see an event, event B, it does not change your probability that you assign to the prior A. So again, let's say the same kind of stupid example that I have my friend outside and they will come now. If I tell you a very kind of irrelevant information, like they're wearing a watch, it doesn't really change your prior belief on how tall they are. So these two are two independent events. And they are different from disjoint events. So two disjoint events are not independent because by definition, if you observe one of them, you will change your perception of the other probability. You'll assign 0 to the other probability. Again, if I see that right now we have a day, the probability of having night is 0. So that's independence. And again, we use this a lot, and this is a very strong assumption. So as you probably can think about some examples, it's really hard to say with 100% that two events are completely independent from each other. But in some cases, especially in machine learning, we assume that the events are independent, even if they are not 100% independent. Okay. Any questions? We're going a little bit fast. Okay, perfect. If you're familiar with this, it's a great sign. Now let's talk about a concept called random variables. So essentially, don't overthink what is a random variable. Random variable is a mathematical mapping or a mathematical function from the sample space to real numbers. So essentially, when we talk about random variables, what we're doing is we are assigning a number to any possible event that can happen. So in a case like rolling a dice, you can have 6 events, 1, 2, 3, 4, 5, 6. So it's very natural to assign the face value as the random variable. So if you see 1, the value is 1. For some other events, like for example, toss of a coin, we can have some sort of a contract between each other. That if I see head, it's going to be 0. If I see tail, it's going to be 1. And for other variables, like for example, the number of the heads, assigning a number to the outcomes is pretty natural and pretty possible. So but the takeaway here is that essentially all you need to know is the notation. So when we talk about random variable, we're essentially talking just about a function that takes the events that can have some sort of a numerical sense or numerical ordering, or they cannot have it, like toss of a coin. And then we just assign a number to them. And by doing this, we can actually define a lot of beautiful things that we will use in future. So just remember one notation because some people might have issue with it. So when I say P of X equal to 2 equal 1/4, you can think of X as being a random variable, 2 as the value that it takes. And then what this whole thing represents, for example, in this example, is having 2 heads. And that's going to be 1 out of 4 possible outcomes. And the other thing that we will see a lot is the difference between discrete and continuous random variables. Some things like, for example, height or maybe even salary are continuous. So whatever 2 values you take, I can divide them by half and tell you another very valid value. But some other events, some other probabilities, they're just discrete or they're categorical. So for example, the number of heads is either 1 or 2. You cannot have 1.5. Okay, so using random variables, the reason that we really like it is that because it gives us this flexibility, it gives us this opportunity to define something called PMF or probability mass function. Right now, we're talking about discrete random variables, but then in the next slide, we're going to generalize it to continuous variables as well. So essentially, the idea is that now whatever event we're having, we can assign a number to it. We can assign a probability to it. But that probability should actually satisfy all those like axioms that we talked about. So they should be between 0 and 1. They should sum to 1 if you add them all together. And by doing this, we can actually define things like this. So this notation is something you will see a lot in this course. So let's break it down if you're not familiar with it. So the left side, we have P and subscript X, which is capital X. And then this is the argument, which is like lower cap X. So this X right here shows that I'm talking about the random variable X. And this X is just the numbers. So it can be, for example, in the previous example, we had 2. And this is essentially equal to P of X, the random variable, taking on the value lower cap X. For continuous variables, we can also do the same thing. So the idea is that now we will assign a value to each point, but you probably realize that at this point we have a big issue. And it's that if you have continuous variables, you probably have infinite number of values that can be valid. And if you assign a non-zero value to it, they will integrate or sum to a value that is infinity, that is more than 1. So to solve that issue, we just define the probability for an interval. So when we say the probability of someone being like, I don't know, 5'9", we don't really exactly mean 5'9". We also accept some sort of an error. So that's why we formally define it like this. So we define it as the random variable X taking on a value that is approximately equal to X with a certain error delta X. Make sense? Any questions? And the reason we do this is because now if you integrate that, it should integrate to 1. And again, remember this from now on until the end of the course, because you'll see a lot of questions and proofs. So whatever you do with the discrete variables, you can also hopefully do it with the continuous variable, but the sum will turn into an integral. So if you're summing over a bunch of values, and then now you're going to go to continuous random variables, you need to change the summation to integration. Okay, any questions? We'll see an example of it in a few seconds. So two important things that we need to discuss is expectation and variance. We can define expectation and variance for like random variables, and it's essentially a tool to give us a sense of the world. So many of the actions that you take, if you ever play a game, if you ever gamble, if you ever invest, are based on these values, based on the expectation and variance. So let's see, what do they mean? So the goal, the motivation behind this is that we have a bunch of different events that can happen. And because of this, we cannot really make a decision. So expectation, for instance, gives us, as the name suggests, an expected value that you will probably see if you are there to take all the actions. So here is how we actually calculate it. It's essentially a weighted averaging. So let's say we have X different outcomes. Let's say we have, for example, 1, 2, 3, 4, 5, 6 for a roll of a dice. So each of these events can happen with a certain probability. Okay, so let's call this P of X. So if we want to take the expected value of a function of those random variables, all we need to do is essentially we need to multiply that function at that X value by the probability of point X. So it's essentially, you can think about it in the first step as some sort of a weighted averaging, and those weights are coming from the probability of the points. So if you ever took a bunch of values and you added them together and you divided them by their number, what you're essentially doing is you're essentially taking some sort of an expectation, but with an assumption. And the assumption is that the probability of observing each of those values is the same thing, and it's equal to 1 over n. We'll talk about this as a specific distribution called the uniform distribution, but essentially this is the idea. So just to give you an example, let's say we're playing a game at casino, okay? So if you win that game, I'm gonna give you, let's say, $50. So you put $50, and if you win the game, I'll give you another $50. So you double your money. And if you lose the game, you'll get 0. So what is the expected value if the probability of winning and losing is the same? It's essentially equal to 0, because it's essentially minus 50 times 1 over 2 plus 50 times 1 over 2, which is just equal to 0. And now if I change that, if I, for example, tell you that, hey, the probability of you winning is now 40%, and the probability of you losing is now 60%. So at this point, you will have a negative expected value. And this is essentially how casinos make money. So in every casino game, if you find the expected value, it's usually something that is better for the casino holders. So for example, there is a game called roulette. You can bet on, for example, like 37 numbers actually from 0 to 36. But if you win, they will give you 36 times your money. However, there are 37 events that can happen. So here, casinos in the long term have an edge. And the idea of expected value is that we'll talk about the law of large number again in a few slides. The idea is that if you do something for unlimited amount of time, what you will get at the end is going to converge to this expected value. And again, as I said, whenever we have discrete and we go to continuous variables, all you need to do is to change the summation to an integration. Any questions about expected value? And this is one of the things that you will see a lot throughout almost all the algorithms, because we define usually our metrics in terms of the expected value. So usually we want to maximize or minimize an expected value. There are some properties that expected values have. So if we assume there is no function, if we just want to find the expected value of our variable x, it's just the amount of that value, x, times its probability, or like averaged by its probability weighted. And the expected value for a fixed distribution or for a fixed probability is always equal to c. So if you do something and you always see one outcome, your expected value of that will be that same outcome always. That kind of intuitively makes sense. And the most important thing that you need to know about expectation is that expectation, if you think about it as an operation, is a linear operation. So essentially, if you have things like this, ag of x plus b times h of x, you can easily reduce it down to some sort of like a linear shape, which is equal to a times the expected value of g of x plus b times the expected value of h. So you can break down the addition to 2. And if you have a scalar multiplied by the expected value, you can draw it out. And this may look very kind of intuitive for some of you. It's probably not. At least in terms of the discrete values, you can easily find it. But the idea is that a lot of models that you see these days, like generate, let's say, images or videos, essentially they are kind of working well because this is true. If the expectation was not a linear operation, all of those models would break. So remember, if in an exam you had a question with expected value and you had something like this, remember it's linear, you can break it down. And we have also something else called the variance. So the idea is that we cannot really make decisions based on the expected values. Because let's say if I tell you that let's play a game together, if you win, I'm going to give you $1 million. And if you lose, I'm going to kill you. So that's probably not a good game because there is a game called Russian roulette. It's exactly like this. So the probabilities are on your side. So expected value of you winning is a lot. But the problem is if you lose, you're going to die essentially in this case. So it's very important to both see the expected value and also the variance in your decision makings. And we also see the same thing in machine learning as well. You sometimes have some models that make very good predictions, but sometimes they make really bad predictions. Usually we don't like those models. They have like a lot of variance. And in some cases, we might even prefer models that have lower expected values, but lower variance. So essentially, you can think about variance as how predictable something can be. And again, as I just gave you an example, it's a very important concept in machine learning. So the definition of variance is, again, is based on the expected value operation. Is the expected value of x minus e of x squared. So if you find the expected value of x minus e of x, it's going to be equal to 0. But if you square that, now you have a different beast, which is the variance. So this is your probably first proof in this course. So if you do some algebraic manipulation, if you find this squared, and if you break it down using the linearity of the expected value operator, you'll end up with a term that looks like this. And this is a very important term. And remember, these two are completely different from each other. As I told you, expected value is a linear operator. So we saw it in the previous years in the exam that some people wrote e of x squared as e of x, the whole thing is squared. It is not. It's a linear operator, but a linear operator cannot actually do that. So essentially, to find a variance, and if you again remember your basic math courses and the way you found variances, this is the way you can do it. You can either get that value, find the expected value, and subtract all the values from the expected value and square it, and then find it. Or you can square each of those expected, like each of those values of x, find an expected value over the squares, and then find an expected value over the actual x values and square that, and then find the difference between them. And that's going to be our variance. So some famous kind of things that you need to know. Again, these are also very important when you're doing some sort of like proof or in a lot of algorithms. You see that we have a term like the variance of a constant, the variance of C. And suddenly you don't see it anymore. And the reason for it is because that is equal to 0. So you can easily use, let's say, this last formula. From the last formula, we can say it's going to be c squared minus c squared, and you'll get to 0. And the other very important thing that you need to know is that the variance of c times x is equal to c squared times the variance of x. So unlike the expected value, variance is not linear. As you can see, if you multiply it by a scalar, the whole thing will not be multiplied by that scalar. It will be multiplied by the square of that scalar or that constant value. Any questions? All good with variance? Perfect. So now let's talk about the things that you'll probably see a lot throughout the course, and it's when we have multi-dimensional probability or high-dimensional probabilities. So remember, we talked a lot about the joint probability of 2 events. Now we can generalize that to n events. So for example, when we are like having an image, when we want to classify an image, this is one thing we do. We assume each pixel of that image is a random variable. So if you have a 30 by 30 image, you have essentially 900 different variables. And we assume that the whole image that we're getting is essentially the joint probability over all of those variables. So what we have in all of the problems that you will be solving this semester is we have a data set, we have a bunch of variables, a bunch of features, and these features, you observe some kind of values in the training set from them. And your job is essentially to kind of find a model that maximizes the probability of seeing those events at the same time, which is called the maximum likelihood, which we will talk about in the next few weeks. So again, think about every problem that you're seeing as being a stochastic, as having some probability distribution. You probably have more than one variable. You probably have n different features and different pixels, or if you have a large sentence, whatever that you are working with. And then your job for like developing a machine learning model is to develop a model that finds these probabilities as best as it can. So that's essentially what we're doing in this course. So it's kind of good to know a little bit about these joint probabilities and how we can actually work with them. The first technique that is a very important technique is called marginalization, or marginal density functions. So let's say you have n different variables and you have access to the joint probability of them. But the thing is, you don't care about that joint probability. All you care about is the probability of just one of the variables, let's say x1. So the way that you can kind of find it is using this technique called marginalization. So essentially, all you do is you will integrate all the other variables. So you take an integral from x2 minus infinity to infinity, x3 minus infinity to infinity, up until xn minus infinity to infinity. So the only variable that you haven't taken the integral from is x1, and then you'll be left with that. Because essentially, if you think about it, when you integrate a variable, you're removing it, kind of. And that's what we call marginal density function. Again, it's very important if you're interested in how images are being generated or any sort of generative model. All we need to do is essentially finding some probabilities, and marginalization is a very important technique here. Any questions? Yes.
So the point PDF, is it the intersection between all of them?
Exactly. So it's the probability of seeing all of them at the same time. So let's say I want to like specify probability of seeing an image of a human. You can think about that as having a lot of pixels. But for now, let's say we just think about the features. So the probability that that person has two eyes or like is like a large probability, right? Or that person has a nose is a large probability. So by having this joint probability, you can actually say that, hey, I am having a model that sees or that assigns a large probability to this image because it sees that, hey, I have a nose, I have two eyes, so then this is a human being. But at the same time, if now you have, let's say, an image of an alien with one eye, then the probability and all the other things are the same as human being. So the thing is that since the probability of having one eye is very low in human beings, you will assign a lower probability to the whole image. So it's essentially the probability of the intersection of everything. Even if one thing is wrong, you will assign a lower probability to the whole thing. And again, just have that in mind because some people struggle to make this connection, especially at the beginning of the course, that whatever we're trying to solve, we see it as a high dimensional variable and a high dimensional probability question. So for example, we see a bunch of data. I think you went over linear regression yesterday. So you see a bunch of data, let's say about a home. So how many bedrooms do they have? How many like how many square feet they are or which neighborhood they're at. These are all different features, what we call them, but we model them using a random variable. And what we're seeing when we have a sample of the data is essentially a sample of this joint probability. So you can see that, hey, I have a, I don't know, like a 4-bedroom home that has this much square feet. And you can also think about this as from the lens of being independent or not. Sometimes some of these variables can be independent, sometimes not. So for example, again, in the example of the home or home prices, the larger a home is, the more chance it has more bedrooms, right? So you cannot really say that they're independent from each other. You cannot really have a 400 square feet, 10-bedroom home, for example. So we'll talk about this a little bit more, but we don't make any assumption at this point about x1 to xn. We don't assume they're independent. We don't assume they're disjoint. And then we will see what's going to happen. So similar to the case of two random variables, we can also define conditional probability for n random variables. So it's a probability of x1 given all the other random variables. And essentially, the formula that you have in the numerator, you have the same thing. You have the joint probability of everything. But this time in the denominator, you have the joint probability of everything but that variable that you're interested in. So if you think about it again, it's as if you kind of just don't care about x1 and you just see what is the probability that I see everything other than x1. And then in the numerator, you see, okay, what is the probability that I can see everything at the same time? And this will give you the conditional probability of x1 given all the other variables. So in the, for example, image generation case, which we will not touch in this class, we have a family of models called autoregressive models, which are essentially generating new images using this idea. So they start from a pixel, like the, let's say the leftmost pixel, and then they say, okay, what is the probability of seeing this pixel 2 given what I saw in pixel 1? And then they go on and build an image that looks like a real image. So it's a very powerful tool, and it's a very powerful thing to know. So in the case of two random variables, again, this will essentially be like the base formula and the conditional formula that you saw. But in the case of like high dimensional probability, if you haven't seen it, this just looks like this. So all that changes is the denominator. So now the denominator will be the probability of everything in the evidence. And another intuition that I can give you is you can think about the probability of observing x2 up until xn as just everything being one random variable. And what essentially we're doing here is the same thing as we did before. Any questions from high dimensional conditional probability? Good, perfect. Now, we have this interesting thing called a chain rule. So you will see this a lot. You will see this a lot because usually we don't have the joint probability. Usually we want to find the joint probability, or we want to find a model that represents the joint probability. And to do that, as I said, in the case of autoregressive image generation models, we usually start from one pixel or from one random variable. We see the value of that, and then we condition everything based on that autoregressively. So just to remember this chain rule, you always start from, let's say, x1. Then the second term will be like x1 is going to be in the evidence, and then it's going to be x2. The third term is always x3 given everything that comes before that. So to remember this formula again, it's at every point you have x1, x2, x3, x4 up until xn. But what you're conditioning these values on will change, and they will essentially be everything that you saw previously. So this is called the chain rule of probability. This is the basis of autoregressive models, and it's a very, very powerful thing because if you think about it, you can just start from one variable, let's say x1, it can be even a random thing, and then you can generate and find some patterns of how an image, for example, is being generated, or how language is generated, actually. So this is kind of the basis of how those language models kind of work. And then we have independence. So again, just like the case of two variables, we can define independent variables for like multiple values and multiple variables. And that's just equal to this definition. So if you have x1 to xn, if you have the joint probability, that will be equal to f of x1, x2 up until xn. Now, if you compare these two, the same intuition that we had is essentially proven again. So what it essentially means that if you have seen x1, it has not changed your perception of x2. So p of x2 given x1 is the same thing as p of x2. Or p of x3 given x1 and x2 is the same thing as p of x3. So n random variables are independent if and only if seeing one of them or seeing a bunch of them does not change our perception about the other ones. And another thing that I wanted to mention here, which is very important, is that you see, generally, E of G times H is not equal to the expected value of G times the expected value of H. This is only true if G and H are independent, okay? So again, think about expected value as being linear. So it's linear, so you cannot really say like things like E of G of X and H equal to E of G times E of H. It's only true if you have this independence assumption. Make sense? Any questions? And be very careful with this, because again, we always see a bunch of students, like maybe like 20% of people in the exams who mess this up. So we don't have such assumption that two variables are independent, but they assume they're independent and they write it like this. It's not always true. And independence, just as a final note on this topic of independence, is a very strong assumption. So when you assume two things are independent, you're making a very, very big assumption. So now let's talk about covariance. So covariance is essentially some sort of like a generalization of variance for like higher dimensional probabilities, but you can also define it for two variables. So again, just like expected value and variance that we define, I can define a new function called the covariance function. So the covariance function is essentially this like term right here. So it's that, so again, you can think about G as being a function of X and Y, or if it's hard for you to see it like that, you can just forget about G, remove all the G's, and you can see E of X and Y, or like the covariance of X and Y. It's essentially the like X and Y value, or a function of X and Y value, multiplied by their joint probability. So again, this is kind of like another expected value, but this time you're kind of assigning the weights based on the joint distribution. Again, for the continuous variables, the summation will turn into an integral, and this is what you get. And remember, the expected value, the covariance, and the variance, they're all scalar values. So they should always be a scalar, just one number. So funny thing about covariance is, again, if you like just see the definition of the covariance, it kind of looks like this. So the covariance is essentially kind of like a cross variance. So you basically have a random variable X, you remove the mean of that random variable, and then you have another random variable Y. You do the same thing and you multiply them together. So just in the same sense that we had for the variance, you can also reduce it down to the E of xy minus E of x times E of y. So covariance is essentially, you can think about it now as some sort of a measure to tell you how two variables are dependent to each other. So if x and y are independent, their covariance is going to be equal to 0. And you know why at this point, hopefully, because E of xy is going to be E of x times E of y. And E of xy here means E of x and y happening at the same time. And that will be 0. So covariance is a tool for us to kind of see how independent two variables are. If it's equal to 0, it's a one way to check that things are independent. Any questions on covariance? We'll talk about covariance matrix in a second. Good? Perfect. So we can also define something called a covariance matrix, and we can generalize this to n random variables. So essentially, a covariance matrix is something like this. In the diagonals, you have the covariance of a random variable with itself. And if you, again, go back to the formula, covariance of x with itself is equal to the variance of x. Because you see, if you change y to x here, covariance of x and x is just the expected value of x minus ex squared, which is the same thing as the variance. So this thing right here, this matrix right here, which we usually show it with sigma, is called the covariance matrix. And it's a very important tool for us to analyze things. Because you see, if you have n different random variables, but just looking at this covariance matrix, you can get a lot of information about how things are. So for example, you can kind of see how dependent or independent variables are, or how scattered a variable is by just looking at the diagonal elements. So a few things to note. The diagonal elements of the covariance matrix, they represent variance. The covariance matrix is always what we call positive semi-definite. So we'll talk a little bit about linear algebra too, but essentially it kind of acts as a positive number. So if you have things like this, which we will talk about it again, X transpose AX. If A is positive semi-definite, this is always going to be greater than 0. And this is a scalar. Again, in the linear algebra part, we're going to talk about this a lot. But that's how we define a positive semi-definite. So if it's semi-definite, it's greater than or equal to 0. And the covariance is always symmetric because the covariance of A and B is equal to the covariance of B and A. Any questions on covariance matrix? And remember this, that covariance matrix is always positive semi-definite, because then we go into some like proofs in linear algebra, and you're probably going to get some questions also in the exam that some like algorithm or some decomposition only works if your matrix is always positive semi-definite. And then you see, oh, my matrix is a covariance matrix, so it's always positive semi-definite. Okay, and let's go to the law of large numbers. So before that, I'm just going to quickly plug in my charger because I'm low on battery. Good. Okay, so do you go? Okay, perfect. Sorry for that. So now let's talk about some concluding remarks. So we're going to talk a little bit about law of large number and then some important distributions. So law of large number is, again, another thing that we assume and we always use without really knowing what kind of assumptions we make. So it's really important to go over it once. So just to kind of give you a sense of what we're talking about, we usually have something called a population. So I can draw it like this. This is our population. And we always assume that this population has some parameters, like, for example, expected value or the mean and a variance that is there, but unfortunately, we cannot find them. The reason for that is because we are unable to sample everything in this population. So again, going back to the example of people's salary or people's height, if you really go on and interview every 8 billion people in the world, you can actually find an actual mean and variance for it. But the problem is you cannot do that. So what we're doing is we are essentially grabbing some samples from this population. So this is, for example, my sample 1. Make sense? So let's say each of these samples that I'm taking have n members or have n samples. So size of n. I can define the average. So again, just to make it more real, let's say I want to find the salary of people in the world. So again, one way for that is literally going over, talking to 8 billion people in the world, finding a number, averaging them, finding their like variance, and then reporting that. These are the true values. So we assume they exist. We can somehow find it, but we are unable to do that usually because of the size or the cost. So what we do is we essentially grab a sample of people of, let's say, 1,000 people. And then we find their salaries and we find the mean of those salaries. So I call that one X bar of n. Make sense? So I have a sample size of n. So I have n different people. I took their average and I got to X of n. So now here is the idea. If I do this sampling multiple times, so if I have one sample that is like this, I have another sample, this. So these are my different samples. So sample 2, sample 3, sample 4. And each of these samples have a size of n. Okay. So what's going to happen is, do you agree that this value, this kind of average of each sample, is probably going to be different from sample to sample? That's kind of an error that I'm having, because depending on which part of the world I'm sampling from, the average salary or the average wage is going to differ a lot. Make sense? Even if I do it in this class, it might differ by some kind of points. Does it make sense? So I can think about this x bar of n as being the random variable itself. Okay, so what is this random variable? It's basically the average of the samples, and I have more than one sample. I have n samples. So the idea of law of large number is this. If you take large enough samples, their expected value, so essentially it's the expected value of expected value of the average. The expected value of x bar of n is going to converge to that actual true mean that I had. So again, if I somehow go to every country in the world and find every population that it represents, find a good sample with a large sample size of them, and I find their kind of averages, like let's say I have a research team in, I don't know, like in Lebanon, I have another research team in France, I have another research team in Mexico. They just go and interview 10,000 people, and they give me the average salary that they found. Now, if I take all of those average salaries myself and I average them together, hopefully I will find a value that is similar or that converges to this actual average salary of all the people in the world. Does that make sense? Okay, good. And the other thing is, now again, as I told you, I have different research teams across the world. They gave me a value, and this is this new random variable that I call it x bar of n. So we saw that the average of that x bar of n is going to hopefully be the actual average. But what about the variance? So remember, we want the variance of this value to be as small as possible so that we have a better prediction. Because if I see that, I don't know, like from one country, I'm getting an average salary of $1,000 a year. From another country, I'm getting $1 million a year. I kind of know that I'm in a very bad position, because if I average them together, it's not really representative of what's going to happen. So the variance of this random variable, ideally, we want it to be as low as possible, so we have the least error. But it's usually going to be behaving like this. So it's going to be equal to the variance of that true population divided by the sample size that I have. So if you look at this ratio, to minimize this ratio, I can do two things. So if I have a problem that inherently have a low variance, like, I don't know, maybe in the terms of like the absolute term, height is a low variance problem. But if I have a high variance problem, like the salary of people in different countries of the world, I already know that I'm going to have a huge variance here as well. The other thing I can do, the other measure that I can do, is to increase the value of the denominator or increase the value of n. And again, you see this in machine learning a lot, that you get a model that gives you some predictions. Again, that prediction is pretty okay-ish, but you are seeing a lot of variability there. So two things you can actually say here. The first thing you can say is that probably my actual problem has a lot of inherent variance in itself, like the salary of people in the world, or I have a small sample size, or I have small samples. So if I train the model for more data points, I'll probably get a better prediction. And essentially, that's what we get. So if you ever did this research and have different teams in different countries of the world, and you saw that, oh, my values are drastically different from each other. So the idea is to either ask people to, hey, please go and grab more people and ask them about their salary, or you should just accept that, hey, this is a high variance problem, and that's the best I can do. And the good thing about it is that you kind of know how bad your prediction is using something called the Chebyshev's inequality. So essentially, it says the probability of you kind of having a very bad prediction. So we define a bad prediction as a prediction which is kind of different from the mean by a tolerance level. So this epsilon right here, we call it the tolerance level, the error that we have. And this is essentially the value that we wanted to predict, which is hopefully very close to this actual mean that we want. So the probability of you having a prediction that is not good is always equal to the variance divided by n epsilon squared. So again, this is what you can kind of see. So again, if you have a high epsilon, if you're okay with a lot of error, then that might be a very good kind of approximator. But if you're not okay with the epsilon, if you make this epsilon smaller, if you want to have a lower tolerance, you see, by definition, you are increasing the probability of having an error. So you need to either compromise on the tolerance or you need to increase the data. Unfortunately, you cannot do anything for this term because it's the variance of the problem of the population. You have no control over it. Any questions for this? And if you have ever done a course on statistics and statistical testing, essentially that whole problem is this. And finally, the last thing that we want to talk about here is that if you kind of have, if you want to find this probability, so the probability of, let's see what it means, is that you have a large sample almost equal to the all people in the world. The probability of that being equal, so limit of that being equal to the actual mean that you're having is always equal to 1. And that is the law of large number. Yes?
Do the samples have to be exclusive?
Oh, not necessarily. So there are different sampling techniques. So there are some hypotheses that are built, or like some kind of inequalities that are built based on the fact that your samples are kind of mutually exclusive from each other. But no, in the real world, there is no need. So essentially, you kind of see this also a lot, that you usually have a very small sample size. You have a very small kind of number of things that you can get. So one way to sample from that, let's say you only have 10 different values. So one way to sample from it is just to kind of sample like different overlapping 3 samples, for example. And that's a very kind of common strategy. Sampling in itself actually requires a course, but we never make this assumption in general that they're independent. There are some sampling algorithms that kind of assumes that, but in general, there is no such requirements. Yes?
Have no control over the variance,
Yeah.
and it's what we're looking for in the overall population, then how can we even use it in the calculation?
That's a good question. So these things, we cannot really use them in our calculations. So what we do is they kind of give us a lower bound, or they kind of like, you see, this thing right here, I cannot really use it. If I could find the actual variance, I didn't really need to kind of do this. One thing that people do is in like, if you've ever taken a statistical course, they usually assume a value for the variance. So for example, they go and find a large sample and say, okay, the variance of this sample size is this. So let's assume that the variance of population is also that. So one way to solve that is we can assume a variance value based on some sample, which is just an approximation. But another way that we use it is something like this. So I now know the dynamic of how this error changes. If I know that I cannot change the variance, then I can change the other 2 things that are kind of in my control. Make sense? Perfect. And the law of large number essentially tells you that if you have a large enough sample, the probability that this thing, essentially the mean of those values converges to the true mean of the population is going to be equal to 1. That's the law of large number. Sounds good? And this should give you an idea that if you're working with any sort of estimation problem, having more values is usually helpful. And finally, let's close this by having some discussion on the famous probability distribution. So uniform distribution is the probably most well-known distribution. So you essentially assume the probability of an event happening is the same thing. So this is how it kind of looks like. It looks like a rectangle. And the probability of each of these points is, so let's say this is A, this is B, it's going to be 1 over B minus A. Because if you take the integral from this, it's essentially the area under the curve, and it's essentially a rectangle. So if your probability is 1 over B minus A, everything fits. The mean value is A plus B over 2, and the variance looks a little bit weird. It's B minus A squared over 12. If you don't know where the 12 comes from, if you take an integral from, again, remember, we had those expected values and integrals. If you take an integral from like x squared, you have a term like x cubed over 3. So that's where the 3 comes in. And yeah, this is all you need to know from each distribution. So from each distribution, we want you to know how it looks like, what it means, and what is its mean, and what is its variance. So essentially, the intuition behind uniform distribution is when we assume the data has a uniform distribution, we are assuming that the probability of observing them is the same. So when you're taking naively the average of a bunch of values, you're essentially assuming a uniform distribution over them. you're assuming that, hey, all of them have the same probability of happening. And that's why when you take the average by adding all the values and dividing them by n, if you have an outlier, your value is going to change a lot. Then we have the Bernoulli distribution. So it's essentially what we call a binary outcome distribution. So you either win or you either lose. So the probability of winning is P. Therefore, based on the axioms, the probability of losing is 1 minus P. So we assume only two things can happen. You either win, you either lose. And then the probability of like you winning is going to look like this. So the mean is going to be P. So essentially the idea is that if the probability of winning a game is 70% of the time, if you do that game enough number of times, if you do that game 1,000,000 times, then you will win 70%. So the more you do it, the closer the mean will be to the actual true mean. And finally, the variance is P times Q. So that will also tell you that how like these things change. So for example, if you have a game that has a 50-50 chance, so it's 1/2 times 1/2, which is 1/4. But if you have another game that is 1/10 and 9/10, so this is going to essentially be 9/10. So this is 10^25. So this is 9/100, sorry. So you can see the kind of closer the values of winning and losing is, the more variance you're having. And that kind of makes sense because like in the extreme case of 1/2, if you see, for example, a toss of a coin, head and tail, you see a lot of variability. But if you have like probability distribution where one of the probabilities are dominant, either winning or losing, you will see less variation in that. So that's kind of the intuition behind P times Q. We also can generalize that to something called binomial distribution. So here we are kind of counting the number of success in independent trials. It's very important. So we assume independence. In things like toss of a coin, that's a very like reasonable assumption. And the way we do it is just using a combinatorics technique. So we just choose X of the n values. And X is basically the number of success. So it's one of the parameters that you need. So you say, okay, I have n trials. I want to win X of them. So the first step is, okay, let's see how many ways I can choose X out of n. And then all I need to do is I need to fill them up with X times success times n minus X times loss, which is 1 minus P. And the mean here is going to be n times P. So essentially, the more you do the trials, the higher your expected value will be. So chance of winning once in 2, for example, the tosses of coin is going to be probably a very smaller value than 1 win in, let's say, 100 tosses of coin, which is kind of literally close to 1. And finally, the variance is going to be n times P times 1 minus P. So as you can see, the mean and variance are independent of X. It doesn't matter how many times you want to win or lose. All that matters is essentially the probability of P, the probability of winning, and the number of trials you're doing. So the more trials you're doing, the higher your mean value will be. And at the same time, the higher your variance will be because you have essentially more chance of seeing something that is like in very kind of different tails. And finally, the most important, which we saved it for the last, is the Gaussian distribution. So this is the most important thing to know really for this course. We make this assumption a lot. So whenever we don't know what is a distribution, we usually assume it's Gaussian. And there is usually a good sort of rationale behind that, because the idea of, if you go back to the law of large number, we just said that, hey, if you assume that the population have like mean and a variance, we can actually fit a Gaussian distribution by only having those two parameters. That's the beauty of Gaussian distribution, because you see, this is how it looks like. It looks a little bit weird if you never worked with it. So it's like 1 over something. So this is for the like one-dimensional case. This is for multi-dimensional case. So as you can see, the covariance matrix, the determinant of covariance comes here. The inverse of covariance is here. It's a little bit weird, but essentially what it does is that it tries to replicate this shape. So in one dimension, it looks like a bell curve. In 2 dimension, it kind of looks like a circle, and in higher dimension, you can Google it and see it kind of looks weird. So the idea is that all you need to do to represent this and to just find these points is a mean vector Again, I'm talking about the multidimensional case. And also the covariance matrix. So by finding the mean and covariance, we can actually find the whole distribution. And that's a big thing. But there are some things that you need to consider. So the Gaussian distribution is symmetric. So if you have an event that is not symmetric, maybe using Gaussian distribution is not a very good idea. So for those cases, you have other types of distributions. The other thing is that the tails are usually very small. So basically, the probability of watching something that is usually more than 3 sigma or 3 standard deviation is usually very, very low. So if you have some events that are what we call heavy-tailed, so the rare events have a high probability of happening, we usually have different distributions. So we have, for example, the T distribution or the student T distribution. Any question on the Gaussian distribution? So for now, 2 things you need to know about it. So know the shape of it, know the formulation for it. And finally, know that by just having the mean and variance, you can represent that. That's a big thing because essentially I'm telling you that, hey, if you give me just 2 values, I can generate 1 billion samples from this distribution, which is a big thing. Good? Yes. Oh, yeah. So think about images again. So we can think about an image as being a probability distribution. Okay, so the images of cats, we can think about it as being a high dimensional probability distribution. So this is just 1 dimension, so you can kind of see it. But in high dimension, it's very hard to see it. Okay, so kind of looks like this. So like this is, let's say, the 2D sort of projection of all possible images. So the cat images, they kind of have a distribution like this. Okay, so they're somewhere right here. Okay, so it's very hard to find this distribution, and it's very hard to kind of localize this distribution because you see you have these bumps here. But for the Gaussian distribution, essentially, when I have a mean and a variance, I can tell you that, hey, you just give me these 2 values, and I can give you the probability of every single point. So for example, just let's go back to the example of the salary, for example. Let's say my x-axis right now is the age, and my y-axis is the salary, okay? So something like this. So if I assume a Gaussian distribution, it means that I'm assuming that at a certain age, let's say 45, you have the maximum, for example, salary that you have, and then the rest of the tail looks like this, okay? So all you need to do is you essentially need to go find a bunch of people, 70-year-olds, 50-year-olds, 40-year-olds, like 5 people in total. And then tell me what is their mean and their variance, okay? And then I'll tell you that, hey, now if you have a new person, like a 26-year-old person that you've never seen a training data like that before, now you can just plug in X into this formula, that's weird formula, and tell me what is their expected salary is and generate a value for that. Make sense? And again, this is another strong assumption. So really just the thing that you need to be very careful about throughout the course is that you're making some assumptions at every step of solving a problem. Just remember what are those and make sure if they actually represent the reality. So if you assume something is Gaussian, you're assuming it has a shape like this, it is symmetric, the tails have a low probability. So these are the things that you need to be careful about. So if you develop the model based on this assumption and it's not working well for non-symmetric data, that's probably the reason. Make sense? Okay. We have one more topic. It takes hopefully less than an hour and it's on linear algebra. So if you don't have any questions about probability, we can switch gears to linear algebra.